Alright, so the other day in lab we got a chance to have the exciting experience of watching ice melt, followed closely by proving that a watched pot does actually boil eventually. Let's take a look at what your graph probably came up with. If you look at how we've laid out the graph, we've got time on the x-axis and temperature on the y-axis, and nice even increments, as you can see, 10, 20, 30, 40, 50, all the way up to our expected range. Alright, so what do we find? Your graph should have looked something like this. Basically, your ice started out a little bit below zero, maybe 10 below 0 Celsius, climbed steadily up to somewhere right around zero, leveled off, and then as the ice turned into liquid water, that water then heated up there right close to 100, but not quite, and leveled off just about there. So what we know is that anywhere below 0 Celsius, you've got a solid, and you saw that because you had solid ice. As that ice melted, in between 0 and almost 100, it was a liquid as water, and then above that temperature, obviously, it's going to turn into a vapor. So what we can infer from this graph here, this flat area right here, this first flat area of your graph, was where the ice was melting, and then the second going from a solid to a liquid, and the second flat area was going from a liquid to a vapor, and that's what we call boiling or vaporization. All right, so basically if you look at a graph like this, you can find two things. You can find the vaporization point or the boiling point. That's where that upper flat area is. And you can also find the melting point or the freezing point. Same thing. Just depends on which direction you're going. If you're warming up, it's the melting point. If you're cooling back down, it becomes a freezing point. And we can see that for water, it's 0 and 100, or at least pretty close. So any graph actually should look like this. You can do this with any substance. So for instance, if we took, say, isopropyl alcohol, and we made a graph of what happened if we started with a solid chunk of isopropyl alcohol, rubbing alcohol, right, and warm that up, you'd have to actually extend the graph down a little ways because it would have to be really cold to be solid. And here's what your graph would look like of a warming chunk of rubbing alcohol. It would warm up from about 100 below 0 Celsius and up to right around here, looks like about in the low negative 80 something range, negative 89 I think is where it is. And then that would warm up, the liquid would warm up all the way up to about 83 degrees is where it seems to level off and stop. It can't get any hotter than 83 degrees because after that it turns to a vapor. Right? So if it's a liquid, once it gets to that boiling point, that liquid can't get any hotter because once it does, it turns into a vapor. So what do we know about rubbing alcohol then? Isopropyl alcohol, we can tell that, oh, there's the vaporization point, the boiling point. And it's right about 83 degrees, and we can also find the freezing or melting point, which is right down there at about negative 89 degrees. So you can do this with anything. You can do this with any substance really, and find its freezing point and find its boiling point. And here they are for water, 0 and 100, which we know. And rubbing alcohol is about negative 89 as its freezing or melting point, and 83 degrees Celsius is its boiling point. We could try it with anything really. Iron, for instance. Obviously, you got to get iron pretty darn hot to get it up to its melting point, 1535 degrees Celsius. Woo. And to get it to actually vaporize and turn into an iron vapor, not just melted liquid iron, but a vapor, 2750 degrees Celsius. That is toasty. So if you look at this, you can kind of figure out where things are. At 20 degrees Celsius, for instance, you're obviously, which is about room temperature, 20 degrees Celsius, you're obviously kind of over on this side of things. So obviously, at room temperature, iron is a solid. If you get it up in between 1500 and 2700 degrees, it would be a liquid if you're in this range. And if you're over 2750, it would be a gas. Right? Same thing up here with water. If it's below 0, if it's over here in this range, it's a solid chunk of ice. At 20 degrees, which is room temperature, you'd be in here, which is a liquid. And if you're over 100 degrees Celsius, that water becomes vapor. Right? Pretty good deal. So there's iron, there's lead. Lead is a little bit lower melting point than iron, which kind of makes sense. If you think of lead, it's kind of a softer metal. It seems like it would melt easier and would vaporize, obviously, a little bit easier too. How about mercury? Huh. At, at room temperature, 20 degrees Celsius, where would you be? Not over here anymore. 20 degrees Celsius would be between these two numbers. So at room temperature, mercury is a liquid. Exactly. So you could freeze mercury into a solid. You'd have to just get it down to negative 39 degrees Celsius, which is pretty cold. That's colder than your average freezer. To get it turned into a vapor, just gotta get above about 357 Celsius. So there's some different metals. How about things that we think of as being a gas, because they usually are. Up here in oxygen, if oxygen is at 20 degrees Celsius, room temperature, it's over on this side, and so it's obviously going to be a vapor. If you could get it down to negative 183 Celsius, which is pretty darn cold, never been that cold on Earth itself, it would turn into a liquid. You could swim around in oxygen. And if you get it down below 219 degrees Celsius, it would actually turn into a frozen chunk of oxygen. How weird would that be? Pretty crazy. Here's one last one just to take a look at. Here's salt water. Now it kind of depends on how much salt you have in the water, but if you've got some just salty water, what it does is actually raises the boiling point up a little bit to a little bit above 100 degrees Celsius, and actually lowers the freezing or the melting point to negative 8 Celsius. So in other words, salt water can actually be below 0 degrees Celsius, and it still will be a liquid. So when, say, you throw some salt on your walkway or your driveway to melt the ice, it could be, say, negative 5 degrees Celsius outside, which is pretty cold. You know, you're kind of down in the, what is that, the low 20s probably, mid to low 20s Fahrenheit. And salt water would actually still be a liquid. So if you were at negative 5 degrees Celsius, you're still in here, it's still a liquid. So it would actually stay a liquid or become a liquid if it was a solid. Pretty cool, pretty handy with salt water. All right, let's talk about bubbles in water. Not those kind of bubbles in water, not the kind you make out of methane. We're talking about bubbles in water when you're boiling it. So let's talk real quick, quick review here of vaporization. When water goes, for instance, from liquid to a vapor, there's two different ways you can do that. Evaporation is one way, and that's just where one little molecule of water at a time kind of pops off the surface of the water. That's the key there, is that the surface is what's losing one little molecule at a time, and over time eventually you lose a few million of those and your water level starts to go down, a few billion of them. Boiling is also a way to vaporize water, to go from a liquid to a vapor, but boiling happens all throughout the liquid, and that's where those bubbles come from. So the bubbles in the water are actually because the water itself is turning from a liquid to a vapor. So if you look at boiling water, you see all those bubbles in there. What are those bubbles made out of? What's inside of them? Well, it's not oxygen or carbon dioxide or hydrogen or anything like that. It's actually inside those bubbles is water. Inside these bubbles right here is water, but it's water vapor. So it's water that's been heated up past 100 degrees, and it then turns, those molecules then get so excited they expand and form a gas. And so those gas bubbles here are actually water in vapor form. And then as they rise up, they release out in the atmosphere or into the room as water vapor. So they're actually made of water. Even though they look like they're air, they're actually water vapor. So where do they come from? How do they form? Essentially, wherever that that water gets to 100 degrees or more, it's going to turn into a vapor. Not just at the surface, like with evaporation, but all throughout down here, they actually form straight into water vapor. Pretty cool. That's what those bubbles are. You see them all the time, and you think, oh, just air bubbles or carbon dioxide or something. But no, it's actually water vapor in those bubbles. And why do they mostly form at the bottom of the container? Well, think about it. Where is most of the heat being applied? Right down there near the bottom. So the bottom generally is where those occur, but they can really form anywhere in the in that whole column of water wherever you have water, and if it's getting above 100 degrees, it'll form a bubble. A lot of times you'll see those bubbles start out kind of small, and they actually get bigger as they go higher because down here there's more pressure from all the water actually pushing down on it, so it squeezes the bubbles smaller, and as they get closer up to the top, there's less pressure on it, and the bubbles actually will grow in size because they're pushing out just as much, but the water's pushing in less. Kind of like when you dive into, say, a swimming pool. If you go down deep, the water's pushing in on your eardrums. You can really feel that, right? And if you go up toward the surface, it's not pushing in as much. So it allows those bubbles to get bigger as they get toward the top of the container. The interesting thing here with our lab is that we weren't able to get our boiling point up to 100 degrees, which is where it should be, right? A nice round number, 100 degrees Celsius, metric system, it's great. Well, here's the problem. What we have above us, at any point, wherever we are on the surface of the Earth, we have a column of air above us that is pressing down on us. Gravity is pulling all these air molecules and pushing it down on us. And at the surface where we are, we say we have 1 atmosphere of pressure. And that atmospheric pressure is pushing down on the liquid in a pot of water, for instance. As the water gets up to 100 degrees, it forms a vapor, and that vapor then becomes the bubble. And the pressure from the water and the pressure from the atmospheric pressure, all that air pushing down on it, keeps that bubble the size it is. Now, if the atmospheric pressure is a lot and it's pushing down a whole bunch, it's harder for those bubbles to then escape out of the liquid. Well, where we live in Sisters, we're quite a ways above sea level, so we actually have, not like, where are we here? This is like North Dakota or something. Okay, then North Dakota. In North Dakota, they might have a full atmosphere of pressure almost because they're almost at sea level. Well, in Sisters, Oregon, we are about 3,000 feet above sea level. It's about 1,000 meters. So we actually have less air above us pushing down. And if less air is pushing down on top of this pot of water, it's going to be easier for that vapor to escape. It's going to be easier for that water to boil. So what does that mean in terms of temperatures? Well, let's take a look at this graph. Here's a graph of somebody made of boiling point versus elevation. So they boiled a bunch of different pots of water at different places, and these are their results. And they kind of fit a nice line through here that seems to indicate that the higher in elevation you go, so here's the elevation, the higher in elevation you go, the lower the boiling point is. In other words, the easier it is to boil the water. So if you are, say, at sea level, that's 0 meters above sea level, obviously, water boils right at about 100 degrees. If you are 4,000 meters above sea level, or let's say 3,000 meters above sea level, that's about the height of South Sister or North Sister, most of the Sisters mountains, right? If you're at 3,000 meters above sea level, water boils at about 90 degrees Celsius. It's just easier to boil because there's less air above you pushing down. In Sisters, the town itself, where we tried to boil our water, and we did boil it, that was about a little less than 1,000 meters, because we're at about 3,000 feet. So about 900 meters, let's say. And where does that put us? Imagine that, right at about 97, which seemed to be right in the range of where most people's water seemed to be boiling, was right in the 97 degree Celsius range. The reason is less air pressure above us from the atmosphere pushing down because we're up higher. So it wasn't that you were inadequate students and couldn't get it up to 100 degrees. There's just no way you could have with water in Sisters. You'd have to go somewhere like Portland or somewhere near sea level to get up to 100 degrees. All right, hope this helps. See you soon.